those being able to write down all the steps in the proof is very critical, because otherwise, there is no reason, or you strictly speaking should not believe any of this unless somebody rigorously proves it to you. So I think my main contribution to this activity was to impress upon Professor Haldane that it's important to spell out all the steps in great detail so that there's no ambiguity left. And this is, I believe that this has been done for the first time through his efforts mainly, and also partially through my efforts, and I'm just displaying some of his efforts. So that basically the proofs that he had written down I had already displayed. So now let me finish off by telling you the ultimate goal of this activity was to find the claim was that if you have a system which conserves the number of right movers separately and the number of left movers separately, then the Green's function of interacting fermions can be calculated exactly. So such systems, systems where the number of right movers are separately conserved and left movers are separately conserved, those are called systems where you have only forward scattering interaction. So that means that so in one dimension, you see, you can only have a right mover or a left mover. The particle can have momentum which is either positive or negative, or zero, of course, but you can have positive or negative. So the thing is that forward scattering is one where after scattering, the momentum continues to be positive. If it was positive earlier, after scattering, if it's still positive, it's called forward scattering. So if it was negative earlier, after scattering, if it's still negative, then you call it forward scattering. If the sign of the momentum changes, then it's called backward scattering. That's like a recoil. So if you ignore those effects of recoil, so that is important. For example, when you have some impurities where the matter waves kind of bounce off the impurity, so you have reflection and transmission. So that's a very important problem which cannot be easily handled by this technique. But if you think about homogeneous interacting Fermi systems where the interaction is purely forward scattering, what is amazing is that even the interacting Fermi theory can be solved exactly. And the Green's function can be obtained in a closed form. And it exhibits what are called, basically it exhibits power law singularities instead of simple poles. So you see, the simple poles are characteristic of what are called Fermi liquids. So whereas power law singularities are a completely qualitatively different class of, it's a qualitatively different ground state other than what we are accustomed to. This is the ground state of a metal, okay? So, or a system of free fermions, for example, that has simple poles. So this doesn't have simple poles, and instead it has branch cuts, so or power law singularities. So when you have such things, then it becomes qualitatively different, and it is classified as a Luttinger liquid by Haldane way back in the famous paper in 1981, Journal of Physics C. So that's where that classification comes from. So, so I'm just pointing out how to use this formalism to calculate the one particle Green's function. And if you remember that in the early part of this lecture series, I told you why it is important to calculate the one particle Green's function, what sort of physical information it embodies, and so on. So I told you that it kind of tells you a lot about the nature of the quasi-particles in the system and so on. So that's the reason why it's important to calculate this, and this is how you would go about calculating. And so the idea is that you write the fermion creation operator for the right movers in terms of those bosons that you have constructed, which through chiral anomaly you have constructed these bosons, and then you just go ahead and state that these are what are called the shift operators. So you recall that this kind of the bosons don't change the total number of right movers, because you see on the other hand, the left hand side is a creation operator, so it really increases the total number of right movers by 1 when you act it on any state, isn't it? Because after all, you're creating a right mover. So the question is that how can you express such an operator in terms of bosons when these bosons are after all number conserving? And the reason is you can introduce a new operator called the shift operator, where you the only role of this operator is to increase the number of fermions by 1. And so the state remains as it is. So in other words, if you start with a ground state of n particles, it gives you a ground state with n plus 1 particle. So it doesn't change the ground state to excited state. Maps the ground state to ground state, except that it increases the number of particles by 1. And this operator commutes with all these other bosons. So it's kind of, I mean, to prove this is not at all easy, and most of the books don't do a good job of doing this. And because I insisted, Professor Hardlin took great pains to prove this correspondence. It's called the Fermi-Bose correspondence. And it's completely non-trivial and very counterintuitive. And it's not at all obvious. And it certainly cries out for a proof. And that too, a very convincing proof. And I explained to him what all things I don't find convincing about the proofs that are there in the literature, and he managed to fix all those loopholes. And so the purpose of this lecture series is to just display all those issues that have earlier versions of, or earlier papers or review articles have not been clear about. And so this lecture series clearly fixes all those issues. Okay, so that was the main purpose of this lecture series. So now you just express, once you know that those are operator, these are operator identities. Remember, these is like this is, so in other words, the matrix elements of the left hand side is the same as matrix elements of the non-local combination of operators. So once that we have established this, we can go ahead and so these shift operators obey these properties, and now is the total number of right movers. So you can go ahead and calculate the Green's function. So this would be basically the hole propagator, because you're first creating a hole and then later destroying a hole, or create a hole and then create a particle. So basically you fill the hole with a particle. So you first create a hole at xt, and then you fill the hole at x dash t dash. So so that's called a hole propagator. And remember that these phi's are not fully related. They are related to NR and the bosons, but the theta commutes with the bosons, but they don't commute with NR. So you have to be careful there. And yeah, so because thetas don't commute with NR, so I have to rewrite this in this fashion. So I use the unitarity property of e raised to I theta r and write it like this. And then I go ahead and use these identities, and now I'm so this factor comes out, and then I just have to calculate this average. And because my theory, or the Hamiltonian of an interacting Fermi system is quadratic in the bosons, and therefore exactly solvable. This average can be calculated easily, because through the cumulant expansion, because only the leading order cumulant contributes. And you can just go ahead and do that. And so remember that I told you that you can rewrite these bosons in terms of other bosons that exactly diagonalize the theory. Okay, so these D1 and D2s exactly diagonalize the theory. So, and these are coefficients which are complex numbers or real numbers which we have already calculated earlier. So given that this is known, you can just go ahead and all these averages are going to be zero. Only these two averages are not zero. So keeping that in mind, you can rewrite so the Green's function, the whole propagator, in terms of these averages. Okay, so you just it's only related to these averages now, and these averages are related to omega is something we have already found, and these numbers we have found. So just to refresh your memory, what are those? Yeah. So this thing will not appear because it's RR propagator. So this will never. We have no occasion to require this. Only we require this sort of thing. Okay. And so this omega is going to be related to, yeah. So remember that omega is just this, and VQ is the, you know what that is, right? So this is the rho R rho L coupling strength, and this is the rho R coupling strength. This is the same as rho L coupling strength. So we can just go ahead and write this. And, so and then that's it. And once you know how to write these things, then the rest of it is very clear. So I mean, if you're wondering why B times B average is zero even for an interacting system, that's an interesting question to ask. See, if you take B and B itself, it's going to be zero because you see the D1 times DQ1 times DQ dash 1 average is zero. And then so is D dagger Q2 D1, that's also zero because after all the D1 and D2 are they're decoupled because they're the ones which diagonalize the Hamiltonian. So the BB averages for the R and R are zero. But for R and L, they're not zero because there's going to be a D dagger Q2 DQ2 average which is not zero. Okay, so there's going to be this which is not zero. So BR average is zero, BL average is zero, but BL is not zero, and neither is B dagger R. No, those are not zero. Okay. So keeping that in mind, this would be the answer. I mean, so basically we have been so you can just work backward and keep substituting. So just go ahead and substitute that, and then you can assume your interaction are short range. Maybe it has some. So you can introduce something called the bandwidth, where the BQ is zero when Q is larger than some maximum value. So it's called the bandwidth. So and then, or you can make the bandwidth infinite, in which case you get logarithmic. So this will be log. It's going to be proportional to the log of x minus x prime minus b times t minus t prime. Okay.
Hello, sir.
Yeah.
Just a minute. I think your slides are stuck. Like, at least for me, I'm not able to see your slides changing.
Can you see now? Are they changing now?
No, not for me. Like, I don't know. What about the others? Are you?
Yes, I cannot. Same here.
Same, right? Yeah, sir. So it is stuck actually, the slides. Can you?
So I'll again share.
Yeah.
Can you see now?
Yeah, yes, now we can see.
Okay. Now is it changing?
Uh, Now it is at slide number 80.
No. I am constantly changing. You cannot make out.
No, it is stuck at slide number 80. That Green's function.
No.
Uh, no, sir, it's still stuck in that slide.
Uh, so I will just show you this way only. This is visible.
Yeah, it is visible now. Yeah, now we can. Yeah, now it's changing. Yeah.
Yeah, the vectors was a problem. So that's it. I mean, I don't want to make a big fuss because it is clear how to do this, because all you have to do is express these creation annihilation of a right movers in terms of the bosons, and they appear in the exponent. And when you take average, it's just the cumulant expansion, because the Hamiltonian is a quadratic in the boson, so you get an exact answer. That exact answer, I haven't evaluated this because then this lecture was mostly about the technical aspects, the mathematical aspects of Bosonization rather than the applications. So the applications will involve working this out explicitly, staring at what it implies and what it means for physics and so on. What is the new physics that is implied by this formula? That what does it tell you about 1D interacting fermions that is different from uh, what you are normally accustomed to. So that would be applications. So this lecture series was mostly about the technical mathematical aspects. It's all about making things rigorous and convincing, so that so there's a reason why I was unconvinced for a long time, which is why okay, let me come to the conclusions, which will probably highlight that part. Can you see my conclusion slide? Can you see my conclusion slide?
Yes, sir.
Okay. So read this. So basically, it says that chiral bosonization is a powerful tool for studying interacting fermions. Uh, okay. When the total number of right and left movers are separately conserved. Okay. You can read that sentence, right? Can you see that first sentence?
Yes, sir.
Okay. So that's the whole point. So this is a powerful tool. It's powerful in the sense that it is so powerful that you can actually write down the exact result. So the exact correlation functions can be obtained if the number of right and left movers are separately conserved. But so even though that is the case, you see, when you have a problem where the number of right and number of left movers are not separately conserved, then it's not possible to write down anything exactly. And in fact, what is even more embarrassing is that a system as simple as three fermions interacting with say a delta function potential, which you solve that's one of the first problems you solve in the first course in quantum mechanics. That itself cannot be solved easily using this technique, because you see that problem does not conserve the number of right movers or number of left movers. It just conserves the total number, because the delta function impurity involves backscattering. So you uh, fermion with positive momentum will, part of it will become its negative value. So you'll have reflection and transmission. So because you have reflection, that problem does not conserve the number of right movers separately or left movers separately. And it is very embarrassing, at least from my point of view, that a technique which claims to be so powerful cannot even handle uh, a problem. So in other words, it maps this problem of free fermions in the presence of a delta function potential to a very complicated non-local sine-Gordon theory. Whereas any undergraduate student of quantum mechanics can solve that problem in no time. So that to me is a tremendous drawback, because Kane and Fisher tried to study the effect of these impurities in a Luttinger liquid in the early 90s, and they used this chiral bosonization technique, and an enormous number of papers, close to probably certainly in the large hundreds, if not the thousands. So physical review letters, they're flooded with papers from the early 90s up to even the present. So they all use this technique of chiral bosonization to study fermions with impurities. When in fact, if you step back and you know, uh, ask yourself, is this really something that you should be doing? Because it cannot even, all it does is it takes a problem with free fermions subject to an impurity and it maps to a sine-Gordon theory. And that is to me quite silly. And that's the reason why in our group we invented something called non-chiral bosonization, where we this Fermi-Bose correspondence, which is a mathematical identity, we took the liberty of modifying that in a way that doesn't affect the the fermion commutation. Remember that if you express the fermion in terms of those bosons, the Fermi fields have to anti-commute. That's the key thing. So you have to respect Pauli principle. But if you express in terms of bosons, it's going to be hard to explain how a expression involving only bosons can anti-commute. That is the whole trick about bosonization. You express it in a very complicated non-local way, so that even though it's expressed in terms of bosons, it still anti-commutes in the proper way. So what we did was we modified this Fermi-Bose correspondence to incorporate impurities right from the start. So in other words, just like that problem of free fermions plus impurities exactly solvable by undergraduate quantum mechanics students, in our non-chiral bosonization also it is equally easily exactly solvable. There is a free fermions plus impurities. It's not mapped to any complicated theory. It's exactly solvable because we modify the Fermi-Bose correspondence in such a way that it incorporates those backscattering effects into the Fermi-Bose correspondence. So now all we do is we switch on the so the backward scattering is only through the only due to the impurities. So because of that, we are able to write down the exact correlation functions even when there are impurities, which is quite remarkable according to me. And with Joy and also Nikhil, we have published close to 8 or 9 papers on that. But yes, still the community is a bit suspicious because there are certain results which they strongly believe, which our theory appears not to agree with. But I think even that is not really true. So that's one of the things we are trying to work out to make sure that some of the key results which those people believe to be absolutely true are also recovered. We have shown that many of the key results are in fact already recovered. And I won't go into that. So that's the reason why this lecture series was not about our technique, which is non-chiral bosonization. So this was about chiral bosonization, and the non-chiral bosonization. The next slide says, well, that's another story. Okay. So thank you for your attention, and if you have any question, I'll answer it. So are there any questions?
So is there anyone who have any question? You may ask.
So if there are no questions, we can stop here. So thanks for attending these lectures, and hopefully Danny will upload the last lecture on my website, and will kind of constitute a complete series on this, on the technical aspects of chiral bosonization. Okay. So if we are done, we can leave.
Okay.
So no questions, we can leave. Okay.
Yes. All right.